Long before the skies were patrolled by birds or even insects as we know them today, the ancient Earth was already home to some of the very first true masters of flight. The dawn of flight marks a transformative chapter in the history of life on our planet, a moment when creatures evolved the remarkable ability to take to the air, changing the dynamics of ecosystems forever. This vast story begins not with birds, but with a group of fascinating reptiles known as pterosaurs, the true pioneers of powered flight during the Mesozoic Era. To understand the origin of pterosaurs and their place among Earth's earliest flyers, we must journey back over 230 million years to the late Triassic period. The world at this time was vastly different than today. The land masses were still clustered in the colossal supercontinent called Pangaea. Climate patterns fluctuated between wet and dry phases, and life forms were in a state of dramatic evolution and diversification following the Great Permian extinction. In this dynamic environment, the first vertebrates to conquer the aerial niche emerged. But flight did not simply appear overnight. It is a complex evolutionary adaptation that required significant anatomical and physiological changes. Before pterosaurs took to the skies, other life forms had attempted gliding or passive aerial movement. Some of the earliest known flyers today include certain ancient insects whose ancestors fluttered tens of millions of years earlier. However, among vertebrates, flight would take a leap forward with the arrival of the pterosaurs. The earliest ancestors of pterosaurs likely evolved from small, agile archosaur reptiles, part of the larger group that eventually gave rise to both dinosaurs and crocodilians. These ancestors exhibited traits conducive to aerial locomotion. Lightweight bones, elongated limbs, and perhaps some form of skin membranes or proto-wings that allowed them to glide short distances, increasing their ability to escape predators or search for food. The fossil record provides a window into this transition. The oldest recognized pterosaur fossils date back approximately 228 million years. These creatures were characterized by hollow bones, elongated fourth fingers supporting wing membranes, and various other unique skeletal modifications that indicate powered flight, not mere gliding. It's important to note that the wings of pterosaurs were formed by a skin and muscle membrane stretched primarily along an extremely elongated fourth digit. Unlike birds whose wings develop primarily from feathers attached to the arms, the evolutionary journey to true powered flight in pterosaurs involved several gradual steps. Initially, small reptiles enhanced their ability to leap and glide between trees in the dense Triassic forests. Over time, natural selection favored individuals with longer wing membranes and lighter builds, culminating in an animal capable of sustained flapping flight. Studies of pterosaur fossils reveal an extraordinary mix of adaptations. Delicate, bird-like bones, but with a distinct arrangement unlike any modern flyers, a keel-shaped sternum to support strong flight muscles, and a lightweight skull designed for aerodynamic efficiency. One of the most fascinating aspects of the dawn of flight is how it transformed the ecological landscape. With flight, pterosaurs could exploit resources inaccessible to terrestrial animals. They became skilled hunters of fish and small vertebrates, adept scavengers, and even specialists feeding on insects or fruit, depending on the species. Flight opened new avenues for colonizing diverse environments, from coastal cliffs and ocean shores to inland forests. While early pterosaurs were usually small to moderately sized creatures, their success set the stage for the remarkable diversity and gigantism of pterosaur species that would dominate the Jurassic and Cretaceous skies. Their ability to launch themselves into the air, navigate wind currents, and maintain energy-efficient flight allowed them to occupy ecological niches that no other reptiles could access. The exact origin story of pterosaurs continues to be a subject of scientific inquiry, with new fossil discoveries refining our understanding of their evolutionary paths. However, what remains indisputable is how these early aerial pioneers demonstrated nature's capacity for innovation, adapting to the challenges of gravity and air resistance to become the very first vertebrates to truly master the skies. As we look more closely at these ancient flyers in the following sections, we will explore the anatomical marvels that enabled flight, the diversity of forms they took, and how these creatures fit within the broader tapestry of prehistoric life. The dawn of flight not only marks a pivotal evolutionary milestone, but also invites us to ponder the extraordinary journey from ground to sky, an enduring testament to life's relentless drive toward exploration and survival. This story of Earth's first flyers is a story of profound transformation, innovation, and adaptation. As we move forward, we will delve deeper into the distinctions that separate pterosaurs from their fellow reptiles, helping us appreciate the unique evolutionary trajectory that led to these magnificent creatures ruling the ancient skies. As we continue our journey through the ancient skies, it is essential to clarify a common point of confusion that often arises when we discuss prehistoric flying reptiles: the distinction between dinosaurs and pterosaurs. While they share a vaguely similar time frame and often capture our imaginations side by side, these groups are markedly different, belonging to separate branches of the reptilian family tree. Understanding their differences enriches our appreciation of both groups and helps unravel the broader tapestry of Mesozoic life. To start, let us consider what defines a dinosaur. Dinosaurs are a diverse group of primarily terrestrial reptiles that first appeared during the late Triassic period, around 230 million years ago. Characterized by a distinctive set of skeletal features, dinosaurs belong to the clade Dinosauria. Their defining traits include an upright stance with legs positioned directly beneath their bodies, a particular structure of the hip bones, and specific features in the skull and teeth. Dinosaurs dominated the land ecosystems for over 160 million years and gave rise to birds, modern-day avian dinosaurs. Pterosaurs, meanwhile, belong to a different group within the archosaurs, close relatives to dinosaurs, but on a distinct evolutionary path. These reptiles were the first vertebrates to achieve powered flight, as we discussed previously, arising roughly contemporaneously with the earliest dinosaurs, but evolving separately. The term pterosaur means winged lizard, and while they often get lumped in popular culture with dinosaurs, this is not scientifically accurate. They are more correctly understood as a sister group to dinosaurs, sharing a common ancestor, but diverging early in the archosaur lineage. A key difference lies in their anatomy and adaptations, especially relating to locomotion. Dinosaurs were almost exclusively terrestrial animals, ranging from massive herbivores like Triceratops and gigantic carnivores like Tyrannosaurus rex, to smaller omnivores and herbivores. Although the ancestors of birds evolved from small theropod dinosaurs that began experimenting with gliding and eventually active flight, traditional non-avian dinosaurs did not possess the specialized wing structures seen in pterosaurs. In contrast, pterosaurs are distinguished by their modified forelimbs, where the fourth finger is dramatically elongated to support a membranous wing that stretched to their hind limbs and body, creating a vast surface area for flight. This wing structure is unique among vertebrates, differing fundamentally from the feathered wings of birds, bats, and their respective ancestors. Their bones are often hollow and thin-walled to minimize weight, another significant adaptation for flight. Beyond their wings, pterosaurs also had notable skull and jaw adaptations that vary widely across species, from long, slender jaws ideal for snatching fish to large crests possibly used for display. Dinosaurs, however, had a wider array of skull shapes adapted for terrestrial feeding strategies, but never developed wings supported by elongated digits. When we explore their habitats and lifestyles, dinosaurs typically occupied niches on land, with some evolving into enormous herbivores or ferocious predators. Pterosaurs, by contrast, were the aerial counterparts, with many species living near coastlines, lakes, or inland waterways, exploiting resources that were difficult for land-bound dinosaurs to obtain. They were expertly adapted not just for flying, but also for landing and walking on land, exhibiting a combination of lifestyles all linked by their capability for flight. It is also important to understand how fossil evidence supports these distinctions. Dinosaur fossils are often found in terrestrial sediments, and their skeletons demonstrate robust limb bones designed to support body weight on land. Pterosaur fossils, however, often appear in coastal or marine deposits, reflecting their affinity for flying near water and feeding primarily on aquatic prey. Their lighter, more fragile bones tell a story of adaptation to the aerial life. Evolutionary relationships further highlight these differences. Both dinosaurs and pterosaurs are part of the Archosauria, ruling reptiles, which also includes crocodilians. Yet within archosaurs, dinosaurs form the clade Dinosauria, separated from pterosauria, their distinct order. Birds are the direct descendants of theropod dinosaurs, while pterosaurs left no living descendants after their extinction at the end of the Cretaceous. From a scientific point of view, conflating pterosaurs with dinosaurs can obscure the nuanced evolutionary pathways that led to the diverse forms of life in the Mesozoic. Appreciating the unique characteristics of pterosaurs, such as their distinct wing structure, flight adaptations, and ecological roles, allows us to recognize them as remarkable and independent evolutionary experiments in vertebrate flight. In culture and media, too, the distinction often blurs. Popular portrayals sometimes group all large prehistoric reptiles under the umbrella term dinosaurs. But as paleontology has advanced, the differentiation has become a crucial foundation in the scientific study of prehistoric life. Museums, documentaries, and scholarly works now emphasize the distinct identities of pterosaurs and dinosaurs, helping to educate the public about their separate evolutionary stories. As we move forward to the next chapter, exploring the Triassic origins of these earliest pterosaurs amid a world in flux, keep in mind the fascinating separations and connections that define these ancient reptiles. Understanding these differences not only clarifies our grasp of prehistoric biodiversity, but also sets the stage for exploring how the first true flyers adapted, survived, and diversified during the Triassic period's ever-changing landscapes. Thus, the boundary between dinosaurs and pterosaurs is both a scientific and conceptual marker, defining two paths of reptilian evolution, one grounded on the Earth and one reigning the sky. With this foundation, we can better appreciate the awe-inspiring flight of pterosaurs, their biology, and their significance in Earth's ancient ecosystems. The Triassic period, spanning from approximately 252 to 201 million years ago, marks a fundamental chapter in the story of life on Earth, a time of rebirth and rapid change following the devastating Permian-Triassic mass extinction, the most severe biodiversity loss our planet has ever witnessed. Within this dynamic and evolving world, the ancestors of pterosaurs took their first evolutionary steps toward conquering the skies. This period of transition and adaptation set the stage for some of the earliest known true flyers, revealing how life rebounded and diversified amid shifting climates, landscapes, and ecosystems. Following the end Permian extinction, which wiped out an estimated 90% of marine species and 70% of terrestrial vertebrates, the Triassic was a time of ecological opportunity and innovation. the survivors were forced to adapt to radically altered environments. Pangaea, the supercontinent dominating Earth's landmass, offered vast interconnected terrain stretching from equator to pole, with a strong seasonal climate and generally arid conditions punctuated by seasonal monsoons. In these conditions, the first archosaurs, the ruling reptiles, rose to prominence. This diverse group included the ancestors of crocodilians, dinosaurs, and, crucially for our tale, pterosaurs. It was within this deep evolutionary context that the initial steps toward powered flight were undertaken by the small, agile reptiles that would become our planet's pioneering aerial creatures. Early pterosaurs likely evolved from basal archosaur relatives, small reptiles that demonstrated traits advantageous for climbing, leaping, and eventually gliding between branches and across gaps in their forested habitats. While fossils from this exact ancestral lineage remain fragmentary and sometimes elusive, the fossil record of early pterosaurs provides tantalizing glimpses into their morphology and lifestyle. One of the earliest and most important genera is Eudomorphodon, dating back to the late Triassic. Discovered in Italy, this pterosaur provides a remarkable window into the anatomy and evolutionary experimentation of early flyers. Eudomorphodon was relatively small, with a wingspan of around 1 meter, but it already exhibited many of the key adaptations required for sustained flight. Hollow bones, an elongated fourth finger supporting the wing membrane, and complex dentition that suggests a diet focused on fish and small aquatic prey. The environment in which these early pterosaurs lived was often coastal or lake-dominated, providing abundant feeding opportunities. Shallow seas and intricate waterways offered resources that early pterosaurs exploited with a combination of flight and foraging skills. Their lightweight skeletons and wing structures would have allowed them to glide over water surfaces and snatch prey with agility and precision. However, early pterosaur evolution was not solely about flight. These creatures also needed to manage the challenges of terrestrial locomotion, walking, launching themselves into the air, and landing safely. Evidence suggests that early pterosaurs had well-adapted limbs that enabled quadrupedal movement on land, using their wings in concert with their hind limbs. This dual adaptation was critical in enabling them to thrive in both aerial and terrestrial contexts. The fossil sites across Europe, particularly from the late Triassic deposits of Italy and Greenland, have been invaluable for understanding this epoch. Greenland yielded fossils of Preondactylus, another early pterosaur genus showcasing primitive features and providing insights into the early diversification and geographic spread of these reptiles. These early species often sported a combination of primitive and advanced traits: small heads with numerous sharp teeth, moderately long tails providing in-flight stability, and sometimes small crests whose purposes are still debated among scientists. Their size was modest compared to later giants, but their evolutionary experiments set many of the functional blueprints that pterosaurs would build upon in the Jurassic and Cretaceous periods. The Triassic world itself was undergoing profound changes. Vegetation was dominated by ferns, cycads, and conifers, forming dense and diverse forests. Competition for food and space was fierce among opportunistic reptiles, synapsids, and amphibians. The rise of early dinosaurs in the late Triassic also created an evolving competitive backdrop, with pterosaurs occupying niches largely inaccessible to their ground-bound relatives. In this intricate ecological dance, pterosaurs carved out their unique domain. Aerial foragers and scouts navigating the skies and coastlines. Their ability to glide and eventually flap their wings expanded their range, allowed them to access patchy resources, and helped them escape terrestrial dangers. Geological records show that the climate of the Triassic shifted repeatedly, with episodes of warming and drying alternating with more humid phases, challenging life forms to adapt or perish. Such variability likely pressured early pterosaurs to develop efficient flight and mobility strategies, ultimately leading to the remarkable flying devices we find fossilized millions of years later. Moreover, the late Triassic extinction, though less severe than the Permian, also impacted terrestrial and marine life, including some archosaurs. Yet pterosaurs, along with dinosaurs, managed to survive and radiate, suggesting a resilience connected to their distinct biological and ecological traits. As we reflect on these early Triassic beginnings, the emergence of pterosaurs is a story of evolutionary innovation, a series of anatomical and behavioral shifts that allowed a lineage of small, agile reptiles to break free from the constraints of land and explore a new dimension, the air. These pioneers were not just passive gliders, but active flyers mastering the challenges of flight, setting in motion a saga that would span the entirety of the Mesozoic. In the next section, we will delve deeper into the remarkable anatomy that supported this aerial mastery, the skeletons, wing structures, and muscular adaptations that transformed pterosaurs from ground dwellers into sovereigns of the ancient skies. Understanding their biology will illuminate how these early creatures evolved to meet the demanding mechanics of flight and thrive in their changing world. The Triassic was indeed the crucible in which the first flying reptiles were forged, a moment of opportunity and transformation, where the boundary between earth and sky was first crossed by the ancestors of pterosaurs. Their story is one of remarkable adaptation amid a world perpetually in flux, a testament to nature's enduring capacity for innovation. To truly appreciate the marvel that pterosaurs were, we must journey inside their bodies, to the intricate skeletons, unique wings, and muscular adaptations that granted them mastery over the ancient skies. Their anatomy was unlike that of any modern flying creature, a testament to nature's ability to produce diverse solutions to the challenge of flight. In this exploration, we will examine how their bones, wings, and musculature combined to create the first vertebrates capable of true, powered flight. At the heart of pterosaur anatomy is a lightweight but remarkably strong skeleton, specifically evolved to optimize flight without sacrificing necessary support for terrestrial life. Most pterosaur bones were hollow, with thin walls reinforced by internal struts or trabeculae that provided strength while minimizing weight. This pneumatic structure, somewhat akin to the hollow bones of modern birds, allowed pterosaurs to reduce body mass significantly, a critical factor to overcoming gravity during flight. Their skulls display extraordinary diversity, from long and slender beak-like jaws to wide, robust skulls, adorned with crests of varying shapes and sizes. These crests, sometimes simple bony ridges, other times elaborate, thin, plate-like structures extending from the head, likely served multiple purposes, including species recognition, sexual display, and aerodynamic functions. Inside the skull, delicate structures housed complex sensory organs, indicating advanced sight and possibly keen spatial awareness. But it is the structure of the wings that defines pterosaurs most strikingly. Unlike birds, whose wings are extensions of the arm with feathers attached along multiple digits, pterosaur wings are supported primarily by a massively elongated fourth finger of the forelimb. This single digit could stretch to huge lengths, with the wing membrane, a thin, flexible web of skin, muscle, and fibers, extending from this finger down to the hind limbs, sometimes connecting all the way to the ankle or even the tail. This membrane was not a simple sheet, but a complex structure, reinforced internally by fibrous bundles called actinofibrils. These provided both tensile strength and elasticity, allowing the wing to maintain shape while flexing during flight. The construction enabled pterosaurs to perform dynamic maneuvers, modulate wing tension, and absorb the forces generated by flapping and gliding. The shoulder girdle and chest bones of pterosaurs further reveal specializations for flight. The scapula and coracoid bones formed a robust unit anchored to an expanded sternum, which bore a pronounced keel, much like the breastbone of modern birds, serving as an attachment point for powerful flight muscles. These muscles enabled rapid, strong wing beats necessary for takeoff and sustained flight. Pterosaur forelimbs combined strength with flexibility. While the fourth finger was highly specialized and elongated to support the wing, the other digits were shorter and often equipped with sharp claws. These were used for climbing, grasping prey, or walking on land. Importantly, the wrist bones were adapted to allow folding and unfolding of the wing membrane, increasing aerodynamic control and protecting the delicate wing tissue when the creature was grounded. The hind limbs played a significant role not only in terrestrial locomotion, but also in supporting the trailing edge of the wing membrane. Some species had elongated femurs and tibiae, allowing long strides while walking or launching into the air. The configuration of the legs and feet suggests that many pterosaurs were quadrupedal on land, using all four limbs to walk, unlike birds which are primarily bipedal. Tail structures varied between species and periods. Early pterosaurs had long, stiffened tails tipped with a vein-like structure, thought to aid in aerial stability and steering. Later species, especially in the Cretaceous, evolved shorter and more flexible tails, relying more on wing shape and body control for maneuvering. Internal anatomy, although less understood due to fossilization limits, might have included a highly efficient respiratory system. The presence of air sacs and pneumatic bones suggests a capability for sustained oxygen exchange, similar to birds, which is essential for the high metabolic demands of flight. Muscular and cardiovascular adaptations would have paralleled this respiratory system to support endurance and agility in the air. Pterosaur integument, the covering of skin and fibers, also played a role in their anatomy. Many species were covered in pycnofibers, hair-like filaments thought to provide insulation and possibly aerodynamic smoothing. These fibers could have also contributed to thermoregulation, helping these animals maintain body temperatures during flight across varying climates. Their mastery of the air, therefore, was not the result of a single anatomical feature, but the harmonious integration of numerous specialized structures. Their wings were flexible yet strong, their skeletons light yet sturdy, their musculature powerful yet efficient. This intricate anatomical arrangement allowed pterosaurs to conquer niches ranging from coastal fishing grounds to inland forests, soaring gracefully or flapping tirelessly to hunt, scavenge, and explore. What is perhaps most striking about pterosaur anatomy is how it reflects an evolutionary path entirely distinct from the birds and bats that followed millions of years later. Where birds optimized feathered wings attached to hands with 3 main digits, and bats stretched their flight membranes between elongated fingers, pterosaurs found success with a wing stretched along a single, hyper-elongated finger, the fourth. This difference reminds us that flight is not a singular invention, but a biological achievement that arose multiple times through different anatomical innovations. In concluding this exploration, the anatomy of pterosaurs reveals a delicate balance between conflicting needs: wings that are light enough to lift, yet strong enough to withstand stresses, structures adapted for flight, but also capable of terrestrial movement, and physiological systems that supplied the energy and oxygen fueling their remarkable aerial abilities. As we move into the next chapter, we will examine the physics that governed pterosaur flight, uncovering how these anatomical marvels translated into dynamics, lift, thrust, and maneuverability, allowing them to become the undisputed aerial masters of their time. Understanding the mechanics behind their wings and muscles will deepen our awe for these pioneers of the skies and their evolutionary legacy. To unlock the mystery of how pterosaurs mastered the skies, we must delve into the fascinating world of flight physics, a complex interplay of forces and anatomical adaptations that allowed these ancient reptiles to achieve powered flight in an era long before the evolution of birds or bats. Flight, at its core, requires overcoming gravity and generating lift and thrust, plus remarkable control and stability, all balanced within the realm of physics. Pterosaurs were pioneers in this domain, evolving specialized structures and behaviors that enabled them to rule the air for millions of years. When an animal takes to the air, it must contend with four fundamental aerodynamic forces: lift, which opposes gravity and holds the animal aloft; thrust, which propels it forward; drag, which resists motion through the air; and weight, the force of gravity pulling it downward. Pterosaurs evolved a suite of adaptations to maximize lift and thrust while minimizing drag and weight, the essence of efficient flight. Central to generating lift was the remarkable wing structure, dominated by an elongated fourth finger supporting a skin membrane stretched taut over the body and hind limbs. This wing membrane, or patagium, functioned as an aerodynamic surface shaped by muscular control and internal reinforcements called actinofibrils. Such a wing could flex, change shape, and respond dynamically to air currents, allowing pterosaurs to optimize lift over varied speeds and maneuvers. The wingspan of pterosaurs varied widely across species, from modest 1 to 2 meter spans in early forms to staggering 10 meters or more in giants like Quetzalcoatlus. Wing shape and aspect ratio, the ratio of wingspan to wing width, made a crucial difference in flight style. High aspect ratio wings, long and slender like a modern albatross, favored efficient soaring with minimal energy expenditure by riding air currents and thermals. In contrast, lower aspect ratio wings, shorter and broader, facilitated increased maneuverability and flapping flight suited for forested or cluttered environments. Taking off is one of the greatest challenges any flying animal faces, especially for large-bodied flyers. Pterosaurs were unique in their launch mechanics, employing a powerful quadrupedal launch system. Unlike modern birds that rely primarily on their hind limbs for takeoff, pterosaurs used coordinated movements of both forelimbs and hind limbs, leveraging their strong winged forearms to push off the ground rapidly and elevate their bodies into the air. This method compensated for their wing size and mass, providing the leverage required to overcome gravity swiftly. Once aloft, pterosaurs had to maintain thrust through wing flapping. Studies of the pterosaur sternum reveal a pronounced keel, a bony ridge for anchoring massive flight muscles analogous to those of birds, indicating a powerful flight stroke capable of generating strong thrust. This enabled pterosaurs not only to glide passively on air currents, but to actively flap their wings for sustained flight, accelerating, maneuvering, and adjusting altitude. Aerodynamic efficiency also dictated the importance of minimizing drag. The streamlined form of pterosaurs, with smooth aerodynamic heads, slender necks, and contoured bodies, helped reduce resistance. Their thin, lightweight bones and the flexible wing membrane further decreased drag, granting them greater speed and endurance. Balancing in flight required sophisticated control of wing surfaces. The actinofibrils embedded within the wing membrane provided structural integrity, enabling the wing to maintain shape under various aerodynamic loads. Pterosaurs could adjust their wing curvature, changing camber to enhance lift or decrease drag depending on flight conditions. Their joints allowed fine-tuned movements that assisted in banking, turning, and stabilizing in variable air currents. Tail structures served as aerodynamic stabilizers. Early pterosaurs possessed long, stiff tails ending in vein-like expansions, which acted much like the vertical and horizontal stabilizers on modern airplanes, enhancing pitch and yaw control. This tail vein helped them maintain stable, straight flight and execute agile turns. As pterosaurs evolved, later species often had shorter tails, relying more on wing morphology and body movements for control. Another fascinating aspect of pterosaur flight lies in the physiological demands. Sustained powered flight requires a high metabolic rate and efficient oxygen delivery. Pneumatic, air-filled bones reduced weight and integrated with air sac systems, similar to those found in birds, facilitating a flow-through respiratory system capable of extracting oxygen efficiently during intense activity. This intricate respiratory adaptation helped fuel the energetic demands of flapping and long flights. Scientists have used techniques from biomechanics and computational fluid dynamics, combined with fossil measurements, to reconstruct how pterosaurs flew. Models suggest they could perform slow, controlled takeoffs and landings, powerful flapping flight, and soaring over long distances. Some species may have used dynamic soaring techniques, exploiting wind gradients above ocean waves, much like modern seabirds, enabling them to travel vast distances with minimal energy. Launching and landing, though, posed particular challenges. Pterosaurs likely possessed strong grasping claws to stabilize themselves during takeoff and ground movement. Their quadrupedal stance and limb design facilitated a balanced, controlled launch and landing sequence, essential for preventing injury and conserving energy. Despite their apparent grace, pterosaurs were subject to the same physical laws as fluttering leaves or airplanes. Wind conditions, wing loading, the ratio of body weight to wing area, and air density, which varies with altitude and temperature, all influenced their flight capabilities. Larger pterosaurs had to balance the risks and rewards of soaring versus flapping, often favoring soaring flight to conserve energy, while smaller species might have relied more on wing beats for quick, agile movements. The evolutionary success of pterosaur flight owes much to the delicate equilibrium they achieved in these physical parameters. Their anatomy and physiology reflect solutions carefully honed over millions of years. Light enough, strong enough, flexible yet stable, capable of navigating the prehistoric skies with skill and endurance. Our understanding of pterosaur flight physics continues to deepen as new fossil discoveries provide more clues and as advances in technology allow detailed aerodynamic simulations. Appreciating these ancient flyers through the lens of physics reveals not just their impressive capabilities, but also the incredible challenge that flight posed and overcame. As we later explore their locomotion on the ground and in the air, we will see how pterosaurs put these physical principles into practice, launching themselves into the vast Mesozoic skies, soaring above oceans and forests, and maneuvering with a finesse that still inspires wonder today. In mastering the forces of flight, pterosaurs not only conquered a new realm, but forever transformed life on Earth. The ability to soar elegantly through prehistoric skies was only one part of the life of a pterosaur. Equally essential were the skills of locomotion once perched on land, the mechanics of launching into flight, and the intricacies of landing safely, all critical behaviors that underpinned their survival and dominance as master aviators of the Mesozoic. In this chapter, we explore the nuanced biological adaptations and behaviors that pterosaurs employed to navigate both air and earth with grace and efficiency. Pterosaurs were far from awkward when grounded. Although the image of these creatures often conjures visions of wide wingspans and aerial prowess, many species were well adapted for movement on land. Contrary to earlier beliefs that depicted them as clumsy and slow, fossil evidence and biomechanical studies now reveal that pterosaurs were agile quadrupeds, walking on all fours with their wings folded neatly along their sides. Their forelimbs did double duty. Not only did they serve as the primary support for flight, with the elongation of the fourth finger supporting the wing membrane, but the other digits were robust and clawed to facilitate climbing, grasping, and secure ground locomotion. The pterosaur hand bore 4 fingers, 3 short digits used for walking and grasping, plus the extraordinarily long 4th finger for flight. On land, these shorter digits, along with the strong hind limbs, allowed pterosaurs to move confidently and with balance. Most pterosaurs employed a quadrupedal gait when walking, using both their forelimbs and hind limbs. Their wrists were uniquely adapted to this function. The wrist bones allowed the wing finger to fold back and the membrane to collapse between the digits when not in use, preventing damage during movement. The forelimb wing finger did not touch the ground. Instead, the palm and shorter fingers bore the animal's weight, enabling efficient strides. The hind limbs exhibited considerable variety, but they generally featured powerful muscles and joints for propelling movement and aiding in launch. Some species show evidence of a digitigrade stance, walking on their toes to allow quick, light steps, while others bore more robust feet suited for stability on uneven terrain. Launching into flight required overcoming the immense challenge of liftoff, especially for the larger species dealing with increased mass. Unlike many modern birds, which rely primarily on their powerful legs to leap into the air and rapidly engage their wings, pterosaurs used a remarkable quadrupedal launch mechanism. This launch system involved a powerful push-off, using both the forelimbs and hind limbs. Skeletal studies indicate that the pterosaur forelimbs were muscular and biomechanically adapted for strong extension, capable of propelling the animal upward and forward. This leap was immediately followed by a rapid, forceful downstroke of their wings, generating thrust and lift in quick succession to sustain ascent. The quadrupedal launch is supported by fossilized trackways showing distinct forelimb and hind limb impressions, and by biomechanical modeling that demonstrates the energetic advantages of using all 4 limbs to vault into the air. This method minimized the risk of ground collision and allowed even giant pterosaurs, some with wingspans exceeding 10 meters, to become airborne with relative ease. Flight itself was a series of finely tuned balances between flapping and gliding. Smaller pterosaurs likely flapped their wings more actively to navigate forest canopies and capture prey, while larger species often employed soaring flight, utilizing thermal uplifts and wind currents to effortlessly cover vast distances with minimal energy expenditure. Landing, much like takeoff, posed significant risks. Safe, controlled deceleration before touching down was essential, particularly for large flyers. Fossil evidence suggests that pterosaurs approached landings with outstretched wings and legs extended forward. Their strong, flexible limbs absorbed impact forces. Additionally, many species were well equipped with sharp claws on their feet and hands that could grip surfaces upon landing, whether rocky cliffs, tree branches, or shoreline rocks. The quadrupedal posture aided them in stabilizing quickly on uneven or slippery terrain. Interestingly, pterosaur flight membranes may have played a role in landing dynamics, acting somewhat like a bird's tail or the flaps on an airplane wing. By adjusting wing shape and tension, pterosaurs could increase drag and slow their descent in controlled ways, reducing the likelihood of injury. The coordination required for takeoff, flight, and landing illustrates a sophisticated neuromuscular system, integrating sensory input and motor control to perform rapid, complex maneuvers. Their large eyes and keen vision undoubtedly contributed to precise navigation and landing, even in low light or challenging environmental conditions. Thus, life on the wing was not merely about powerful flight muscles and expansive wings. It was an orchestration of anatomical adaptations and behaviors finely tuned to balance the demands of both aerial mastery and terrestrial survival. Pterosaurs were truly remarkable creatures, living bridges between earthbound and airborne realms, navigating waters, cliffs, forests, and open skies with skill and elegance. In the following section, we will reveal the incredible diversity among pterosaurs, from the tiny, insectivorous species flitting through the underbrush to the colossal giants soaring high above the ancient oceans, each adapted to its own niche, yet all united by the shared legacy of flight. Their diversity tells a story of evolutionary experimentation and success, highlighting the boundless creativity of life in the age of flying reptiles. As we broaden our view across the vast expanse of the Mesozoic skies, it becomes clear that pterosaurs were not a monolithic group, but a dazzling array of species, each uniquely adapted to its environment and lifestyle. Their diversity, which spanned over 150 million years, reveals an extraordinary evolutionary tapestry, a gallery of forms ranging from the modestly sized insect hunters to colossal giants rivaling the largest birds that have ever lived. Exploring this diversity deepens our understanding of how flight shaped their biology and ecology, and highlights the remarkable adaptability of these ancient winged reptiles. The earliest pterosaurs of the late Triassic were generally small, with wingspans around 1 to 2 meters. Species like Eudomorphodon and Priondactylus represent the earliest known flyers, often sporting sharp teeth and relatively lightweight bodies to aid in agile flight over coastal waters or forest canopies. These small pterosaurs likely hunted insects, small fish, and other small prey, relying on quick maneuvering and bursts of flapping flight. Their modest sizes allowed them to exploit niches that required agility and precision. Moving into the Jurassic period, pterosaur diversity expanded significantly. We begin to see a variety of morphological adaptations that reflect differing flight styles and ecological roles. Species such as Rhamphorhynchus sported long tails with diamond-shaped vein tips, aiding in aerial stability, while others like Dimorphodon had shorter tails and more robust builds. Wingspans ranged from around 1 meter up to several meters, accommodating both swift flyers and more robust species adapted for soaring or slower flight. Some Jurassic pterosaurs developed elaborate cranial crests, possibly for display or aerodynamic functions. The variety in skull shapes and tooth arrangements points to diversified diets, from fish and insects to small vertebrates, indicating that pterosaurs occupied multiple tiers within their ecosystem. Their wing configurations adapted accordingly, balancing the needs of takeoff, maneuverability, and endurance. The Cretaceous period unleashed an explosive diversification in both the size and form of pterosaurs, leading to some of the most spectacular flying reptiles ever discovered. Among these were the Ajdarchids, a family that includes some of the largest known pterosaurs. Genera, such as Quetzalcoatlus and Hatzegopteryx, boasted wingspans often exceeding 10 meters and extraordinary height when standing, comparable or even surpassing modern-day giraffes. These giant soarers exhibited long necks and beaked skulls, well-suited for a versatile diet likely involving scavenging and hunting small to medium-sized animals. Their enormous wings were shaped for soaring flight, capable of covering great distances by exploiting thermal currents, minimizing energy expenditure. Despite their size, biomechanical studies suggest they were surprisingly agile on land, capable of walking quadrupedally with grace. In contrast to the giants, the Cretaceous also saw the persistence of small to medium-sized species adapted for more specialized niches. Zungaripterids, for example, developed robust jaws and teeth for crushing hard-shelled prey like mollusks, while pteranodontids sported large, streamlined wings perfect for over-ocean soaring and fish hunting. Their skeletal and wing variations accommodated differences in flight style, from dynamic flapping to efficient gliding, demonstrating evolutionary experimentation driven by ecological opportunity. Among these marine and coastal hunters, some pterosaurs evolved distinctive cranial crests, elaborate headgear that may have played roles in sexual selection or aerodynamic stabilization during flight. The shapes of these crests varied dramatically, from thin, blade-like extensions to broad, swooping plates, adding a visual spectacle to their impressive aerial displays. The immense variety in wingspan, body structure, and ecological adaptations across pterosaurs highlights the evolutionary pressures and opportunities presented by their environments. From the dense Triassic forests, where nimble early pterosaurs flitted after insects, to the clear Jurassic skies where soaring specialized forms dominated, to the open Cretaceous oceans teeming with fish and other marine life, pterosaurs evolved to fill nearly every possible airborne niche. This diversity also reflects varying reproductive and social behaviors. The size range implies different strategies for nesting, parental care, and mobility. Smaller species could have nested in concealed locations, while larger pterosaurs required expansive territories. The presence of sexual dimorphism in crest size and shape suggests complex social interactions, possibly including visual displays and intraspecific competition. When we look at the fossil record as a whole, remarkable discoveries continue to enrich this gallery. Fossils from sites spanning North America, Europe, Asia, and Africa reveal regional differences, with some species endemic to certain areas, while others had widespread ranges, highlighting shifts in paleogeography and climate over millions of years. In essence, pterosaurs can be seen as nature's soaring experiment, an evolutionary story of adaptation, innovation, and diversity in flight. Their forms ranged from the delicate and diminutive to the gigantic and formidable, each species telling a unique story about the challenges and triumphs of life on the wing. As we proceed to examine specific early pterosaur genera, such as Eudomorphodon and Dimorphodon, we will uncover more details about their anatomy, ecology, and behaviors, setting the foundation for understanding how the earliest flyers set the course for the breathtaking diversity to come. The gallery of pterosaurs is both magnificent and instructive, offering insight into how flight shaped the ancient world and influenced the path of vertebrate evolution. As we delve into the realm of early pterosaurs, the spotlight falls on some of the most fascinating and revealing genera that paved the way for the evolutionary success of these flying reptiles. Among these, Eudomorphodon and Dimorphodon stand out as iconic representatives, offering a window into the early experimentation and adaptation that characterized pterosaur evolution during the late Triassic and early Jurassic periods. Their fossils, discovered in varying locales, have provided critical clues about the anatomy, behavior, and ecological roles of the first true masters of flight. Eudomorphodon, whose name means true double-formed tooth, is one of the earliest and best-preserved pterosaurs known to science. Discovered in the late Triassic marine deposits of northern Italy, this relatively small pterosaur, typically sporting a wingspan around 1 meter, exhibits complex dentition that suggests a highly specialized diet. Its teeth were heterodont, meaning there were different types of teeth suited for grasping and slicing, pointing to a piscivorous lifestyle focused on catching fish and possibly small marine invertebrates. The skeleton of Eudomorphodon reveals key adaptations for powered flight: hollow bones to reduce weight, a well-developed sternum for anchoring flight muscles, and an elongated fourth finger supporting a broad wing membrane. Its long tail, stiffened with bony rods, likely functioned as an aerial rudder, aiding in flight control and stability. Eudomorphodon's fossils also preserve impressions of soft tissues, offering rare glimpses into wing membrane structure and pycnofiber covering, hinting at insulation or aerodynamic smoothing. Dimorphodon, meaning two-formed tooth, provides another fascinating chapter in early pterosaur history. Found primarily in early Jurassic formations in England, Dimorphodon earned its name due to the presence of two distinct types of teeth in its jaws: large, fang-like teeth at the front for grasping prey, and smaller, sharper teeth towards the back for processing food. This dental differentiation suggests a diverse diet, possibly including insects, small vertebrates, and fish. Broader and more robust than Eudomorphodon, Dimorphodon had a wingspan reaching up to 1.5 meters, featuring a proportionally large head with a strong and shortened skull. Its skeleton shows robust bones and powerful limb musculature, indicative of strength and agility both in flight and on land. Its relatively short tail, compared to the very long tail of Eudomorphodon, may have reflected a shift toward improved maneuverability in more wooded or cluttered environments. Both Eudomorphodon and Dimorphodon illuminate the evolutionary experimentation during the early evolution of flight. Their varied teeth, body sizes, and anatomical features suggest that early pterosaurs occupied a range of ecological niches. Some may have hunted over coastal waters, snatching fish from the surface, while others hunted insects and small prey among forested landscapes. This diversity underscores a fundamental principle. Flight offered not just freedom of movement, but access to a broad diversity of habitats and feeding strategies. Besides these two well-known genera, several other kin in the late Triassic and early Jurassic hint at the breadth of early pterosaur diversity. Priondactylus, another late Triassic species from Italy, showcases primitive features including a long tail and finely toothed jaws, indicating an aquatic or semi-aquatic lifestyle. Anorognathid's, smaller and more compact pterosaurs found in Jurassic sediments, exhibited short skulls and broad wings, adapted perhaps for swift, agile flight in dense forests and insectivore. These early pterosaurs also demonstrate important behavioral and physiological traits. For instance, evidence suggests they were capable climbers and walkers, with limb and claw morphologies suited for grasping and arboreal navigation. This terrestrial competence complemented their aerial skills, enabling them to move efficiently between trees and open air. One of the critical evolutionary advances in these early forms was the refinement of the wing membrane and its attachment patterns. Soft tissue fossil impressions reveal a complex patagium with intrinsic fibers and muscular components allowing fine control during flight. This wing structure contrasts with modern flyers and underscores the unique evolutionary path pterosaurs followed. Together, Eudomorphodon, Dimorphodon, and their kin represent the fascinating phase of evolutionary experimentation that laid the groundwork for later pterosaur diversity. Their fossils inform us not only about form and function, but also about the ecological dynamics of the late Triassic and early Jurassic. The challenges and opportunities that shaped their flight and lifestyle adaptations. As we prepare to move forward into the Jurassic period's skies, these early pioneers remind us that the mastery of flight is a story of many steps and many forms, a story of trial, adaptation, and success that would ultimately lead to some of the most extraordinary creatures ever to take wing. The Jurassic period, spanning from about 201 to 145 million years ago, represents a golden age in the history of pterosaurs, marked by remarkable biological advancements and diversification that elevated these creatures to true mastery of the skies. This era witnessed profound evolutionary refinements in pterosaur anatomy, physiology, and flight capabilities, enabling them to explore new ecological niches and expand their aerial dominance across a world undergoing dramatic environmental change. During the Jurassic, the breakup of Pangaea began in earnest, slowly opening new oceans and modifying climate and habitats. These changes created a mosaic of environments that pterosaurs skillfully exploited, from lush, dense forests to extensive shorelines and inland waterways. As terrestrial and marine ecosystems flourished, so too did the diversity and complexity of pterosaur species. One of the most significant biological advancements of Jurassic pterosaurs was the refinement of wing structure and flight mechanics. Wings became more aerodynamically optimized. The membrane was better supported by intricate internal fibers and musculature, allowing increased flexibility and control. This enabled diverse flight styles, from powerful flapping enabling quick takeoffs and agile maneuvers to impressive gliding abilities for energy-efficient soaring. Jurassic pterosaurs such as Rhamphorhynchus highlight this period's evolutionary innovations. With a wingspan typically around 1.5 meters, this genus possessed a long, stiff tail ending in a diamond-shaped vane, functioning as an aerial stabilizer and rudder to aid in precise flight control. Its teeth were adapted for catching fish, indicating strong connections to marine or freshwater environments, where it likely skimmed over water surfaces or dived for prey. Another notable Jurassic group, the early pterodactyloids, began to emerge in the late Jurassic. These creatures showed several transformative features that would eventually define later pterosaurs: shortened tails, elongated metacarpals, bones in the hand, and often large cranial crests. Their reduced tails improved agility, and stronger wing bones allowed for larger wing surfaces and enhanced flight power. The growing prominence of these pterodactyloids marked a pivotal shift from the basal, long-tailed forms to more advanced flyers. Key Jurassic genera such as Scaphognathus exhibited robust bodies with broad wings, possibly suited for slower, maneuverable flight within forested landscapes, hunting insects, and small vertebrates. Meanwhile, species like Campylognathoides had aerodynamic profiles suggesting powerful, sustained flight over open areas. This variety illustrates how pterosaurs diversified and specialized to occupy different aerial niches. Beyond wing enhancements, skeletal and muscular improvements underpinned better flight performance. The sternum, where powerful flight muscles anchor, became more keeled and specialized, providing greater attachment area and mechanical advantage. This supported more vigorous wing beats, necessary for controlling larger wings and enabling extended flights. Neurological evolution likely paralleled these physical changes. While direct evidence of brain morphology is rare, cranial fossils show expanded brain cases and well-developed optic lobes. These features suggest increases in sensory processing and coordination, vital for precise navigation, hunting, and social signaling in flight. Social behavior and display also became more complex during the Jurassic. Elaborate cranial crests, bony or soft tissue extensions, are found in multiple species and are hypothesized to serve functions in mate recognition, species identification, or even aerodynamic roles. Whether flamboyant or subtle, these display structures hint at rich social interactions and possibly territorial behavior. The ecological roles of Jurassic pterosaurs were equally varied. They served as predators, scavengers, and even possible frugivores, feeding on fruits and seeds. This adaptability was aided by dental and jaw variations, with some pterosaurs having sharp, conical teeth for fishing, while others possessed broader jaws or specialized teeth for crushing or slicing. Fossil trackways from this period offer additional insight, revealing that terrestrial locomotion was efficient and often quadrupedal, with pterosaurs using all four limbs to walk and run on land. Such dual competence in both air and ground movement exemplifies their versatility and evolutionary success. The Jurassic pterosaur story, therefore, is one of dynamic innovation, where flight evolved from a fledgling ability into sophisticated mastery, anatomy became optimized for multiple behaviors, and ecological diversity skyrocketed. This period laid the foundation for the explosive radiation of pterosaurs in the Cretaceous, paving the way for giants to soar and for varied adaptations to thrive worldwide. In looking ahead, we will soon explore that Cretaceous explosion in detail, the time when these creatures reached their largest sizes and broadest ecological dominance. But before that, the Jurassic skies remind us that the evolution of flight is never static. It is an ongoing dance of adaptation, challenge, and transformation carried on the wings of these remarkable reptiles. The Cretaceous period, spanning from approximately 145 to 66 million years ago, marks an epoch of unparalleled transformation and diversification among pterosaurs. Often described as the Cretaceous explosion with respect to these flying reptiles, this era saw the rise of some of the largest and most majestic creatures ever to grace the skies, as pterosaurs attained physical dimensions and ecological dominance previously unmatched. This chapter reveals the breathtaking evolutionary journey that propelled these ancient masters of flight to astonishing sizes and propelled them into new biological frontiers. The transition into the Cretaceous brought significant global changes. Continental drift was fragmenting the vast supercontinents into smaller land masses, seaways expanded, and climates shifted to warmer, more humid conditions. These shifts created a variety of newly accessible habitats, ranging from rich coastal environments and shallow epicontinental seas to expansive forests and floodplains where resources abounded. For pterosaurs capable of flight, this diverse mosaic of ecological opportunities provided an expansive aerial arena to conquer. One of the most striking features of the Cretaceous pterosaur fauna was the emergence and radiation of the agile, a family distinguished by their enormous size, long necks, and often toothless, elongated beaks. These giants, such as the iconic Quetzalcoatlus and Hatzegopteryx, pushed the boundaries of vertebrate flight with wingspans sometimes exceeding 10 to 11 meters, comparable to a small airplane. Their sheer scale invites awe and fascination, yet also provokes deep questions about the biomechanics and lifestyles of such colossal flyers. Quetzalcoatlus northropii, discovered in North America, is often emblematic of this size revolution. Despite its giant wingspan, recent studies indicate that it was likely well adapted both for flight and terrestrial movement. Its long legs and feet suggest it was capably quadrupedal on land, stalking prey much like modern storks or ground hornbills. Far from being merely an aerial giant, Quetzalcoatlus may have been an active predator or scavenger, utilizing both soaring flight to travel vast distances and terrestrial locomotion to hunt small vertebrates. Similarly, Hatzegopteryx thambema from what is now Transylvania exhibited a robust and muscular build, suggesting a different ecological niche, likely adapted for dealing with larger prey and ambush tactics. This demonstrates the ecological complexity and regional diversity of Cretaceous giant pterosaurs, underlining their role as apex predators or versatile opportunists. The mechanics of flight at such colossal sizes required profound anatomical specializations. Bones remained hollow and reinforced internally to balance weight and strength. Wing membranes had to be both resilient and flexible to endure colossal forces during takeoff, soaring, and maneuvering. Flight muscles were well developed and anchored to extensive keeled sterna, supporting powerful wing strokes necessary for launching and sustained flight. Interestingly, the method of launch likely retained the quadrupedal mechanism seen in earlier pterosaurs, enabling these giants to catapult themselves into the air despite their mass, drawing on their muscular forelimbs and hind limbs in a coordinated burst of power. This contrasts with the bipedal takeoffs typical of birds, highlighting the unique evolutionary trajectory of pterosaurs. Aside from the Ajdarchids, a diverse array of other pterosaur groups flourished in the Cretaceous. Pteranodontids, with their distinctive large cranial crests and toothless beaks, were exceptional over-ocean flyers specialized in fish catching. Their elongated wings and streamlined bodies favored dynamic soaring along coastlines and above open waters, similar in ecological niche to modern albatrosses. Additionally, Desungaripterids demonstrated robust jaws and specialized dentition suited for crushing hard-shelled prey like mollusks and crustaceans, often along shoreline or river delta environments. Their unique feeding adaptations present yet another example of how Cretaceous pterosaurs diversified anatomically and ecologically. The period also witnessed evolutionary experiments with cranial ornamentation. Some species developed elaborate crests out of bone or extended soft tissues, sometimes extending from the snout or skull in wildly intricate shapes. These likely served functions in sexual display, species recognition, and communication, complementing their aerial lifestyles. Together, the Cretaceous pterosaur assemblages demonstrate not only spectacular physical gigantism, but also a rich tapestry of ecological specialization. By occupying diverse roles such as soaring marine piscivores, terrestrial stalkers, crushing shoreline feeders, and social displayers, these creatures adapted intricately to their environments. However, this explosion of diversity and size also came with ecological pressures. The concurrent rise of birds, including highly efficient flyers, introduced competition in many aerial niches. Additionally, evolving predatory dinosaurs and changing climates imposed further selective forces, shaping pterosaur evolution toward the end of the Cretaceous. In the grand arc of Earth's history, the Cretaceous pterosaurs represent a crescendo, where evolutionary innovation reached its dazzling peak before the abrupt extinction event that closed the Mesozoic Era. Their reign as the largest flying animals underscores nature's remarkable potential for biological innovation and adaptation. As we proceed, our exploration will bring into focus these colossal giants in detail, illuminating their biology, behavior, and ultimate fate within the ancient ecosystems. The age of the largest flying creatures is a story of supreme evolutionary achievement and poignant transformation, echoing with the beating wings of creatures that forever changed the dynamics of life in the skies. In the grand theater of prehistoric life, few creatures inspire awe quite like the colossal giants of the pterosaur family, the true apex flyers of the Mesozoic skies. Among these titans, Quetzalcoatlus and Hatzegopteryx stand as monuments to nature's capacity for scaling the limits of vertebrate flight. Their immense sizes, powerful anatomies, and ecological dominance provoke profound questions about the biology of flight, terrestrial movement, and survival strategies at gigantic scales. This chapter explores these apex pterosaurs, illuminating their biology, lifestyles, and the mysteries that continue to surround them. Quetzalcoatlus northropi, often heralded as the largest known flying animal, soared during the late Cretaceous of what is now North America. Its wingspan is estimated to have reached an astonishing length of 10 to 11 meters, akin to a modern small airplane. Despite its immense size, Quetzalcoatlus exhibited the quintessential pterosaur anatomy: hollow, lightweight bones, an elongated wing finger supporting a vast membrane, and a strong, keeled sternum anchoring powerful flight muscles. Functionally, its anatomy suggests a remarkable balance between aspects of flight and terrestrial competence. Unlike purely aerial animals, Quetzalcoatlus is believed to have been a proficient quadrupedal walker and runner when on land. Its long legs and sturdy feet imply it could stalk prey, engaging in terrestrial hunting behaviors reminiscent of large modern storks or ground birds. This dual adaptation allowed it to bridge the realms of air and land, exploiting a wide range of ecological niches. Its skull and beak present another fascinating aspect. Toothless and elongated, the beak was likely used to forage efficiently, capturing small vertebrates or scavenging carcasses. The lightweight, streamlined skull contributed to aerodynamic efficiency without compromising feeding capability. Some paleontologists suggest Quetzalcoatlus used a combination of ambush and opportunistic feeding strategies to sustain its large energy requirements. Across the globe, Hatzegopteryx tambema from late Cretaceous Romania offers a contrasting giant with its own distinctive traits. While similar in estimated wingspan to Quetzalcoatlus, Hatzegopteryx's skeleton was notably more robust and muscular. Its skull, unusually broad and heavily built, suggests adaptations for overpowering larger prey or engaging in more forceful feeding behaviors. This reinforces the idea that even among colossal pterosaurs, ecological diversity was vast, with species occupying various niches ranging from nimble aerial hunters to terrestrial predators. The soaring capabilities of these largest pterosaurs reflect incredible evolutionary achievements. Supporting such size in flight demanded exceptional anatomical adaptations. Bones were extremely pneumatized, filled with air spaces, to minimize weight. Wing membranes consisted of resilient fibers capable of withstanding immense aerodynamic forces, and muscular systems provided the immense power necessary for launch and sustained flight. Takeoff mechanics for these giants likely relied on the unique quadrupedal launch technique seen in smaller pterosaurs. Coordinated powerful pushes from the forelimbs and hind limbs catapulted them into the air, overcoming gravity despite their massive bulk. This launch strategy underscores a fundamental divergence from birds, which primarily use their hind limbs. Flight dynamics would have involved a heavy reliance on soaring, exploiting thermal updrafts and wind currents to cover great distances with minimal energy expenditure. Their wing shapes suggest high aspect ratios, favoring gliding and static soaring over extended flights. Maneuverability, while perhaps more limited than smaller species, would still have been sufficient for navigation and hunting. Fossil evidence also hints at complex behaviors and social interactions. Large size may have influenced mating displays, territorial disputes, and nesting strategies, though direct evidence remains scarce. The formidable presence of these giants would have impacted contemporary ecosystems profoundly, influencing prey populations and competing with other large vertebrates. Despite their dominance, the very size that epitomized their success may have contributed to their vulnerability during the end Cretaceous extinction event. Environmental upheavals and shifting ecosystems could have strained their specialized adaptations, leading to the disappearance of these extraordinary creatures. Quetzalcoatlus, Hatzegopteryx, and their kin represent the zenith of pterosaur evolution, merging biological prowess with breathtaking scale. Their stories echo through time as symbols of evolutionary innovation, challenging our perceptions of the limits of flight and the interplay between form, function, and environment. As we continue, we will explore how these apex pterosaurs, along with their smaller relatives, employed diverse feeding strategies to thrive, illuminating the rich tapestry of survival and adaptation that characterized the age of flying reptiles. The survival and success of pterosaurs throughout the Mesozoic era depended not only on their mastery of flight, but also on their incredible versatility in feeding strategies, which were finely tuned to their morphological adaptations and ecological niches. As we examine the diverse diets and hunting behaviors of these ancient flyers, we uncover a complex and fascinating picture of evolutionary innovation, one that showcases how pterosaurs were able to exploit land, sea, and air resources in a variety of ways, ranging from active predation to scavenging and surface skimming. A fundamental aspect of pterosaur feeding strategies was the incredible diversity found within their jaws and dentition, or sometimes the lack thereof, reflecting specialized diets adapted to particular environments. Early pterosaurs, like the late Triassic Eudomorphodon, had teeth well suited for catching fish. They possessed numerous small conical teeth with different shapes within the same jaw. A heterodont dentition designed to grip slippery prey effectively. Their sharp teeth were perfect tools for snagging fish from the water's surface or shallow margins, indicating a piscivorous lifestyle closely tied to aquatic habitats. As pterosaur evolution progressed into the Jurassic and Cretaceous periods, feeding strategies became increasingly specialized. Some groups, like the rhamphorhynchids, retained sharp, peg-like teeth configured for gripping fish or small animals, while others evolved different adaptations that optimized survival in their ecological niches. Particularly famous are the pteranodontids, toothless pterosaurs characterized by long, pointed beaks and large wingspans. These creatures were expert fish hunters, often depicted soaring above ancient oceans and diving to snatch prey from the water. Their beak shape, broad wings for dynamic soaring, and streamlined bodies suggest a lifestyle remarkably similar to modern seabirds, such as pelicans or gannets. Without teeth, their beaks functioned with precision and speed to seize fish, and the absence of teeth reduced weight, aiding their long-distance flights. Another significant feeding adaptation is found in D-Sungaripterids, pterosaurs, with robust jaws and specialized crushing teeth. These pterosaurs likely inhabited coastal or lagoon environments where they fed on hard-shelled prey, such as mollusks, crustaceans, and other shellfish. Their jaws exhibited strong bite forces, and their teeth were broad and rounded, perfectly suited for crushing dense shells. This indicates a benthic feeding strategy, foraging along the seafloor or tide pools. Some smaller pterosaurs, like the anurognathids, had short, broad skulls filled with tiny teeth, suggesting an insectivorous diet. Their flight style allowed quick, agile maneuvers to catch airborne insects, making them the aerial equivalent of modern bats. This strategy would have been highly successful in forested environments rich in insect prey. In addition to hunting, scavenging likely played a vital role for various pterosaurs, especially the larger species. The very large azhdarchids, including giants such as Quetzalcoatlus and Hatzegopteryx, with their powerful beaks and long legs, may have foraged on carcasses, exploiting carrion much like modern vultures. This dual approach, active predation combined with opportunistic scavenging, would have maximized their dietary options in diverse and sometimes resource-scarce environments. One particularly intriguing feeding method is surface skimming, a technique in which the pterosaur flies low over water bodies, dipping their lower jaws or beaks into the water to catch fish or amphibians. While no direct modern analog exists among reptiles, some interpretations of fossil morphology, such as the shape of the lower jaw and adaptations in sensory structures, suggest that certain pterosaurs may have engaged in a similar behavior, analogous to the feeding habits of today's skipjack or skimmer birds. This would require delicate balance and precise control during flight, supported by their evolved wing and neck musculature. Besides the jaws and teeth, the heads of many pterosaurs bear striking crests and other cranial ornamentations, which might have played indirect roles in feeding. These crests could act as stabilizers during flight, reducing drag and helping maintain balance while hunting or skimming close to the water surface. In some species, sexual dimorphism in crest size may have also indicated maturity and competitive fitness, correlating with feeding territories. Beyond anatomical adaptations, pterosaurs' flight capabilities themselves enhanced their feeding strategies. Their ability to soar effortlessly over vast distances enabled them to exploit widely scattered food resources, from coastal waters to inland areas. Speed and maneuverability allowed for capturing elusive prey, while long flights and excellent vision aided in the search for carrion or migrating schools of fish. This remarkable range of feeding adaptations highlights the pterosaurs' role as essential components of their ecosystems, functioning as predators, scavengers, and even insect controllers. Their diverse diets and methods illustrate how flight expanded not only their mobility, but also their ecological flexibility. Understanding these feeding strategies also sheds light on their interactions with other prehistoric creatures. Pterosaurs occupied complex food webs, competing and coexisting with dinosaurs, early birds, fish, and marine reptiles. Their diets and hunting behaviors evolved in response to changing environments and biotic pressures, a testament to their resilience and innovation. As we continue our exploration, we will soon examine the pterosaurs' life beyond the skies, focusing on their terrestrial locomotion and behaviors on land. But the story of feeding strategies remains a fantastic window into the ingenuity with which these flying reptiles exploited the ancient world, balancing the demands of flight with the necessities of survival in diverse and dynamic Mesozoic landscapes. While pterosaurs are often celebrated for their remarkable aerial abilities, their life was not confined solely to the skies. Understanding how these creatures moved and interacted with the land reveals a critical aspect of their biology and ecology. Ground movement, including walking, running, and launching into flight, required specialized adaptations that balanced their requirements for both terrestrial mobility and effortless flight. In this section, we explore the fascinating mechanics and anatomical features that allowed pterosaurs to live dual lives, masters of sky and confident movers on land. Contrary to earlier depictions that showed pterosaurs as awkward or clumsy on solid ground, modern studies reveal that many pterosaurs were efficient quadrupeds when on land, walking on all four limbs with surprising agility and coordination. Their distinctive forelimbs, adapted to support expansive wings, also served as functional limbs for walking. This dual functionality is a remarkable example of evolutionary compromise, where the demands of flight powerfully shaped terrestrial locomotion, yet did not prevent effective movement on land. The pterosaur forelimbs were unique in their structure. The four shorter fingers ending in strong, curved claws supported the animal's weight during walking, while the extraordinarily elongated fourth digit was reserved exclusively for supporting the wing membrane. When walking, the wing finger folded back against the limb, and the patagium collapsed neatly, avoiding interference with the ground surface. This allowed pterosaurs to bear weight on their palms and shorter digits, providing a stable base for locomotion. Fossil footprints and trackways have been instrumental in refining our understanding of pterosaur locomotion. These trackways demonstrate typical quadrupedal walking patterns with distinct imprints from forelimbs and hind limbs, clearly indicating coordinated use of all four limbs during terrestrial movement. The stride lengths and limb postures reflected by these traces suggest that pterosaurs were not only walkers, but sometimes capable of quick movements or short bursts of running, especially when threatened or launching into flight. The hind limbs varied in form, but generally possessed features associated with erect, efficient locomotion. In many species, particularly the larger and more derived pterodactyloids, the legs were long and strong, with digitigrade feet standing on toes that ended in sharp claws. These adaptations afforded them balance and traction on a variety of surfaces: rocky shorelines, forest floors, and perhaps even sand or mud flats. Differences in limb proportions and robustness among pterosaurs hint at ecological variability. Some were adapted for agile terrestrial movement, possibly hunting small prey or scavenging on land, while others might have been less terrestrial, spending more time airborne or perched. For instance, Ajdarshid pterosaurs, like Quetzalcoatlus, had long limbs suggesting an efficient walking gait over terrestrial environments, possibly stalking small vertebrates, much like modern storks or ground birds. Launching into flight from the ground was possibly one of the most demanding behaviors for pterosaurs, especially the larger taxa. Ground launch involved a highly specialized quadrupedal push-off, where the animal simultaneously thrust off the ground using both forelimbs and hind limbs. This contrasts with birds, which typically rely largely on their powerful hind limbs to initiate flight. Pterosaur forelimbs, reinforced and muscular, generated the dominant upward thrust, aided by the leg muscles, catapulting the animal into the air. This mode of launch demanded strong and flexible joints, particularly in the shoulders and wrists, and a durable musculoskeletal system capable of withstanding the mechanical stresses of takeoff. Fossil evidence of robust pterosaur forelimbs and well-developed muscle attachment sites supports this model, highlighting the evolutionary innovation within this group. Landing, too, required delicacy and control. Pterosaurs are thought to have approached landing by extending their forelimbs and hind limbs forward, using their sharp claws and muscular limbs to absorb impact forces and stabilize their bodies. They likely landed in a quadrupedal stance, minimizing stress on any single limb and facilitating a stable touchdown. The surfaces on which pterosaurs moved ranged from coastal beaches and rocky cliffs to forest floors and inland plains. Their limb morphology, claw shapes, and inferred muscular strength indicate adaptability to varied substrates. Some species may have been able climbers as well, able to grasp branches or rocky outcrops, adding vertical habitat to their range. In essence, pterosaurs were not only airborne wanderers, but creatures with versatile locomotion capable of efficient land movement. Their ability to walk, run, and launch in coordinated ways allowed them to exploit a wide array of environments and resources, from pursuing prey on land and water to nesting and resting safely on solid ground. This terrestrial competence complemented their aerial life, underscoring the complexity of pterosaur biology. As we move forward, our attention will turn to their reproductive behaviors and nesting strategies, providing further insight into how these extraordinary reptiles balanced life in the air with critical life stages spent on the earth below. Breeding and nesting represent some of the most intimate windows into the lives of extinct creatures, revealing behaviors, social structures, and evolutionary strategies that go far beyond bones and wings. When it comes to pterosaurs, the story of their reproduction, parental care, and family life is both intriguing and complex, shedding light on how these extraordinary flying reptiles navigated the challenges of raising their young amid the ancient skies and landscapes. The fossil record provides striking evidence that pterosaurs laid eggs, much like modern reptiles and birds, and many fossilized nests have been discovered offering direct insights into their reproductive biology. Some nests contain multiple eggs, often laid in simple arrangements within shallow depressions in sandy or muddy substrates, suggesting they returned to specific breeding grounds. These nesting sites, such as those found in the late Cretaceous deposits in China and Argentina, reflect social behaviors that may have included colonial nesting, with many individuals congregating close together. Pterosaur eggs themselves are remarkable. They were relatively small compared to the adult sizes, with leathery, pliable shells rather than hard, calcareous ones like those of many birds. This indicates a reproductive strategy that favored flexibility and perhaps partial incubation within the nest or by the parents. The soft shell also suggests that pterosaur embryos may have developed in moist or partially buried environments to prevent desiccation, much like modern reptiles. Developmental studies of fossil embryos and hatchlings have revealed that many pterosaurs were precocial, able to move and perhaps even fly shortly after hatching. This contrasts with the altricial young of many birds, which require extensive parental care. Fossilized hatchlings show well-developed wings and limb bones, supporting the idea that young pterosaurs could have been relatively independent quickly, capable of feeding themselves soon after leaving the nest. However, this doesn't preclude significant parental investment. Evidence suggests that pterosaurs, especially some species, engaged in forms of parental care. Adults may have guarded nests and offspring, protecting vulnerable young from predators and environmental hazards. Certain bone beds preserve groups of juveniles and adults together, hinting at social family units or at least periods of association. The notion of family structures gains credence from the diversity of pterosaur species and their ecological contexts. It is likely that reproductive strategies varied widely, from more solitary species relying on nest concealment to those that nested in colonies, benefiting from communal protection and social interactions. Some species probably had seasonal breeding periods aligned with environmental cues to maximize offspring survival. Sexual dimorphism may have played a role in reproductive behaviors, especially in species with elaborate cranial crests or other ornamentations. These features could serve as signals during mating displays, helping individuals select mates and establish dominance or territory. Such complex social interactions imply a sophisticated behavioral repertoire connected with their reproductive cycle. The study of pterosaur growth patterns further enriches this narrative. Analysis of bone histology shows rapid growth rates in juveniles, likely necessary to quickly reach sizes that reduce vulnerability. Among some species, prolonged juvenile phases suggest extended periods of parental or social support, while others exhibit swift maturation, supporting a diversity of life history strategies. These reproductive and social traits present fascinating parallels with both reptiles and birds today, underscoring pterosaurs' place in the broader story of vertebrate evolution. Despite their extinction, their legacy of reproductive adaptation offers a window into the endurance of life's strategies across deep time. As the tale of pterosaurs continues, their breeding and nesting behaviors remind us that they were not mere isolated flyers of the past, but complex creatures with nuanced lives, invested in the survival of their lineage and shaped by the ancient world's rhythms. Next, we will explore the remarkable textures and coverings of pterosaurs, their skins, pycnofibers, and the ongoing debates about their thermoregulatory adaptations, further enriching our understanding of these majestic ancient aviators. Beneath the majestic wings and delicate skeletal frames of pterosaurs lay another fascinating layer of their biology: their skin and integumentary structures. These coverings not only protected the ancient creatures, but also played significant roles in insulation, thermoregulation, camouflage, and perhaps even social signaling. Among the most intriguing discoveries about pterosaurs in recent decades has been the recognition of pycnofibers, fine, hair-like filaments that may reveal critical insights into how these reptiles lived and thrived in diverse prehistoric climates. This section ventures into what science currently understands about pterosaur skin, the nature of pycnofibers, and the lively scientific debate surrounding their function, especially in the context of insulation. For many years, the perception of pterosaurs was of smooth-skinned, almost amphibian-like reptiles. Because their fossilization rarely preserves soft tissues, the texture and coverings of their skin remained elusive. However, exceptional fossil sites, notably in China and parts of Europe, have yielded impressions and even detailed preservation of pterosaur skin and integument. These fossils reveal that pterosaur skin was notably thin and leathery, often studded with small scales or tubercles. Unlike the overlapping scales of many modern reptiles, these were often granular and irregular, providing some protection without adding weight or limiting flexibility. Given their need for agile flight, retaining lightweight and pliable skin was crucial. Yet perhaps more revolutionary has been the discovery of pycnofibers, fine, filamentous structures covering the bodies of diverse pterosaur species. First described in fossils from the Middle Jurassic to the late Cretaceous, these filamentous hairs resemble primitive body coverings seen in theropod dinosaurs and are considered by many paleontologists to be homologous to the early stages of feathers, or at least analogous insulating coverings. Pycnofibers vary in length, density, and complexity. Some fossils show simple hair-like filaments, while others reveal branching or tufted structures. These fibers likely served as insulation, helping to retain body heat and suggesting that pterosaurs may have been endothermic, or at least maintained elevated metabolic rates, contrary to the traditional view of all reptiles as cold-blooded. The debate over the exact nature and function of pycnofibers is robust and ongoing. Some researchers argue that pycnofibers primarily functioned as thermal insulation, critical for flight endurance in cooler climates or high altitudes. Others propose that they had additional roles in sensory perception, camouflage via coloration or patterns, or even in display and species recognition. Interestingly, the presence of pycnofibers aligns pterosaurs closer to birds and certain feathered dinosaurs, hinting at a deeper evolutionary relationship and convergent adaptations related to flight and metabolism. This challenges simplistic categorizations and opens new perspectives on the evolutionary pathways of integumentary structures. While direct evidence of coloration is rare, some fossils preserve microscopic melanosomes within pycnofibers, suggesting pterosaurs could display vivid colors or iridescence. Such coloration would have important implications for communication, sexual selection, and environmental adaptations. The skin membranes of wings, meanwhile, are known to have been thin, flexible, and highly vascularized, allowing gas exchange and efficient thermoregulation. These wings lacked feathers but contained actinofibrils, internal fiber bundles providing structural support and elasticity. The interplay of skin and pycnofibers created a delicate balance between durability, lightweight function, and thermoregulation. Further fascinating is the potential sensory function of integumentary structures, with some hypotheses suggesting pycnofibers could detect airflow or tactile stimuli, enhancing flight control and environmental awareness. Research into pterosaur integument remains a vibrant and evolving field, leveraging new fossil finds and advanced imaging technologies like synchrotron scanning and electron microscopy. These tools continue to refine our understanding of pycnofiber morphology, arrangement, and evolutionary significance. In conclusion, pterosaur skin and pycnofibers present a compelling story of adaptation, revealing creatures much more complex and dynamic than previously imagined. These coverings likely enabled thermal balance, enhanced flight efficiency, and facilitated social interactions, elements crucial to the survival and proliferation of pterosaurs across varied climates and epochs. As we move forward, we will explore pterosaur sensory worlds, their vision, intelligence, and social behaviors that further illuminate how these extraordinary reptiles thrived in the ancient skies and beyond. Pterosaurs, Though often remembered primarily for their awe-inspiring flight capabilities and spectacular forms, possessed a suite of sensory and cognitive adaptations that reveal their complex behaviors, keen perception, and intricate social lives. Understanding their vision, brain structure, and social interactions paints a richer and more nuanced picture of these ancient aviators, showing that mastering the skies also demanded keen senses and intelligent responses to a dynamic world. From fossil evidence and comparative anatomy, it is clear that pterosaurs had exceptional vision. Well-preserved skulls reveal large eye sockets, or orbits, often filled with large sclerotic rings, bony structures inside the eye indicating the presence of large and sophisticated eyes. Such anatomy suggests pterosaurs had excellent eyesight, crucial for navigation, hunting, and social signaling in the three-dimensional environment of the air. Their eyes were likely adapted for acute detecting of movement and fine detail, enabling them to spot prey from considerable distances or detect subtle changes in their environment. For species hunting fish or insects, sharp visual acuity would have been vital in timing and precision. Additionally, large eyes support the idea that some pterosaurs could have been crepuscular or even nocturnal, navigating in low-light conditions during dawn, dusk, or at night. Braincase fossils, while rare, have afforded paleontologists glimpses into the structure and relative size of pterosaur brains. Endocasts, or internal molds of the brain cavity, reveal that pterosaurs had relatively large brains compared to their body size, particularly in regions associated with vision, motor control, and coordination. The well-developed flocculus, a brain region critical for balance and eye movement coordination, supports their ability to maneuver adeptly during flight, maintaining equilibrium and responding to rapidly changing aerial conditions. These neurological features point to sophisticated sensory-motor integration, allowing pterosaurs to perform complex aerial maneuvers, regulate wing position, and modulate flight in response to environmental stimuli. This level of brain organization hints at higher cognitive functions than often assumed for reptiles, perhaps including learning, memory, and problem-solving useful in hunting and social contexts. Social behavior in pterosaurs, while harder to reconstruct, is inferred from multiple lines of evidence. Fossilized bone beds occasionally reveal groups of pterosaurs preserved together, indicating possible flocking or colony behavior. Breeding grounds with multiple nests suggest communal nesting habits, while the presence of elaborate cranial crests and ornamentations in some species point to visual displays used in mate recognition, competition, or communication. Sexual dimorphism, indicated by differences in crest size and shape between individuals, further implies social complexity, with males and females possibly using crests for courtship and hierarchical dynamics. Such displays would have played a major role in reproductive success and social interactions, signaling fitness or territorial claims. Vocal communication remains speculative, but anatomical studies of the vocal tract suggest pterosaurs may have produced calls or sounds for communication, possibly akin to modern birds or crocodilians. Complex social animals often combine visual and auditory signals to coordinate behaviors, and pterosaurs, sharing evolutionary kinship with archosaurs, may have possessed similar capacities. In addition to sensory and social sophistication, pterosaurs likely exhibited parental care behaviors, supporting survival of their offspring. Fossil evidence of juvenile and adult proximity and nesting sites aligns with the possibility of learned behaviors, protection, or group dynamics involved in rearing young. Altogether, the insights into pterosaur vision, brain anatomy, and social behavior contribute to an image of these reptiles as not just mechanical flyers, but as intelligent, perceptive beings, well equipped to navigate complex environments. Their sensory acuity and cognitive capabilities were integral to their ecological success, enabling them to exploit niches in skies crowded with other evolving vertebrates. As we progress, the next chapter will consider their interactions within ancient ecosystems, the dynamic web of prey, rivals, and environments that shaped their lives. Such ecological interplays underscore the profound connections between anatomy, behavior, and the living world throughout Earth's history. The ancient skies and landscapes that pterosaurs inhabited were complex, dynamic ecosystems teeming with life, each organism playing a role in a tightly woven web of interactions. To fully appreciate the ecological significance of pterosaurs, we must explore their relationships with prey, competitors, predators, and the environments that shaped their evolution and survival. These interactions illuminate how pterosaurs functioned as integral components of Mesozoic ecosystems and reveal the challenges they faced amid shifting biological and geological conditions. At the core of their ecological role were pterosaurs' feeding relationships. As we've seen, their diets varied widely, from small insects and fish to hard-shelled marine invertebrates, and even scavenged carrion. This dietary diversity allowed them to exploit multiple niches across terrestrial and aquatic environments. Coastal and freshwater habitats, with abundant fish populations, were especially vital, attracting numerous piscivorous pterosaurs, such as rhamphorhynchids and pteranodontids. Their adept flight enabled them to scout large areas for food and to access both aquatic and terrestrial prey. In freshwater and marine settings, pterosaurs often interacted with contemporary marine reptiles like ichthyosaurs and plesiosaurs. While these reptiles typically occupied deeper waters, pterosaurs exploited surface waters and shorelines, minimizing direct competition, yet sharing the same trophic webs. Occasionally, diet overlap may have led to competition with fish and diving birds, particularly in the late Cretaceous, when birds became more ecologically prominent. Terrestrially, smaller pterosaurs acted as insectivores, or small vertebrate predators, feeding on insects, amphibians, and juvenile reptiles. These interactions linked pterosaurs to the forest floor and understory, making them important regulators of insect populations and contributors to food chain dynamics. Their role as prey to larger carnivorous dinosaurs and crocodiliforms also shaped their behavior, flight alertness, and possibly social groupings. Pterosaurs faced diverse competitors and predators. Large theropod dinosaurs presented both predatory threats and ecological competition, especially for juvenile or grounded individuals. Fossil evidence from bite marks and regurgitated bones suggests predation pressures, influencing pterosaur nesting behaviors, flight patterns, and habitat preferences. Other vertebrate flyers, such as the emerging birds in the late Jurassic and Cretaceous, carved overlapping niches, leading to complex evolutionary interactions that may have pressured pterosaurs to adapt in feeding and flight strategies. Environmental factors strongly influenced ecosystem interactions. Climatic fluctuations, sea level changes, and habitat fragmentation throughout the Mesozoic created shifting landscapes and resource availability. Pterosaurs adapted by diversifying habitat preferences, from coastal lagoons and river deltas to inland forests and open plains, each environment presenting distinct prey assemblages and competitors. The ability to traverse different habitats by flight gave pterosaurs a remarkable flexibility, unmatched by many terrestrial vertebrates. Additionally, pterosaurs likely played significant roles as both predator and prey in ecosystem dynamics. Their hunting activity helped regulate fish and insect populations, while their eggs and juveniles served as food resources for various carnivores and scavengers. Some large ajdarchids might also have influenced terrestrial food webs, through their predatory or scavenging behaviors. Symbiotic and commensal interactions remain speculative but intriguing. It is conceivable that some pterosaur species engaged in mutualistic relationships, such as cleaning symbioses or feeding alongside large herbivorous dinosaurs, capitalizing on prey disturbed by their movements. In sum, pterosaurs were dynamic participants within their ecosystems, integrated into a constantly evolving network of interactions. Their roles as predators, prey, competitors, and environmental responders highlight the complexity of prehistoric life and the adaptability inherent in the pterosaur lineage. As we advance to the following chapters on global distribution and biogeography, it will become apparent how these ecological interactions varied across continents and environments, shaping the evolutionary pathways and diversity of pterosaurs worldwide. Their ecological narratives underscore the rich interdependence that characterized ancient ecosystems, reminding us that flight was but one facet of their extraordinary existence. The story of pterosaurs is one that spans continents, oceans, and diverse climates, woven intricately into the fabric of Mesozoic global ecosystems. Understanding their global distribution requires examining the fossil record from all corners of the ancient world, revealing how these flying reptiles occupied a vast range of environments and how their biogeographical patterns evolved over millions of years. This section explores the key fossil sites, patterns of dispersal, and regional adaptations that paint a vivid picture of pterosaur biogeography. Pterosaur fossils have been discovered on every continent except Antarctica, from the earliest Triassic localities to the final Cretaceous deposits. Their remains are preserved in an astonishing variety of geological settings, including marine sediments, lake deposits, river floodplains, and even desert environments, reflecting their ecological versatility and ability to exploit diverse habitats. This widespread fossil record makes pterosaurs one of the most globally distributed groups of prehistoric vertebrates. Some of the most important early pterosaur fossils hail from late Triassic and early Jurassic formations in Europe, especially Italy, the United Kingdom, and Germany. These sites have yielded specimens like Eudomorphodon and Dimorphodon, providing insight into the earliest stages of pterosaur evolution in predominantly coastal and forested ecosystems. Northern Africa and North America also contain early Jurassic pterosaur deposits, expanding knowledge about their distribution across Pangaea's western margins. The Jurassic period saw the spread and diversification of pterosaurs into new regions. Key sites such as the Solnhofen limestone in Germany, famed for its exquisite fossil preservation, have produced numerous pterosaur specimens, including Rhamphorhynchus and Pterodactylus. These well-preserved fossils allow detailed studies of anatomy and behavior, showcasing pterosaurs' adaptation to lagoonal environments alongside diverse marine life. Cretaceous pterosaur fossils are found in remarkable abundance and diversity. South America, particularly the Santana Formation in Brazil, has produced some of the most spectacular and complete specimens, including fruit-eating tapagerids and enormous ajdarshids. These fossils demonstrate evolutionary advances in skull ornamentation, feeding strategies, and flight capabilities. Asia, especially China and Mongolia, has become a hotspot of pterosaur discovery, revealing numerous species from early to late Cretaceous formations. The Chinese Jehol biota and surrounding regions have yielded important specimens displaying fine details of soft tissue preservation, including evidence of pycnofibers and wing membranes. This expanding fossil record reveals remarkable diversity, including both small, agile forms and giant soarers. North America is notable for an array of late Cretaceous pterosaurs. The Hell Creek and Canadian Bear Paw formations have produced giant ajdarchids like Quetzalcoatlus, echoing the ecological dominance of pterosaurs as apex aerial predators. Coastal and inland deposits show pterosaurs thriving in a variety of habitats, reflecting adaptability to both marine and terrestrial environments. Africa and Europe also feature Cretaceous pterosaur deposits, with fossils ranging from toothed pterosaurs specialized in fish-eating to the toothless, crested pteranodontids. European formations in Romania exhibit giant pterosaurs, indicating faunal exchanges across ancient land bridges and widespread distributions. Biogeographical patterns in pterosaurs have revealed interesting evolutionary and ecological trends. During the Mesozoic continental drift, sea level changes and climatic fluctuations influenced dispersal routes and isolated populations, fostering regional diversity and speciation. Island formations, mountain ranges, and shifting coastlines acted both as corridors and barriers. Pterosaurs demonstrate both cosmopolitan distribution, evidenced by continual presence in widespread regions, and endemic evolution, with certain lineages restricted to particular continents or ecosystems. For example, tapagerids flourished primarily in South America and Asia, while ajdarchids had a near global reach but exhibited unique species assemblages across continents. Fossil biogeography also reveals shifts in community dynamics over time, with some groups declining as others rose. The appearance and radiations of birds toward the end of the Cretaceous coincided with changes in pterosaur diversity and distribution, suggesting ecological competition or niche partitioning. In sum, the fossil record of pterosaurs maps a rich biogeographical history of evolutionary success and adaptation across the ancient globe. Pterosaurs were not constrained to isolated regions, but were highly mobile and responsive to changing environments, ultimately shaping and being shaped by the Mesozoic world's ecological complexity. As we move forward, the story turns toward the twilight of the pterosaurs, the succession of extinction waves that marked their decline and final disappearance, a poignant conclusion to an extraordinary chapter in the history of flight. The story of pterosaurs, spanning over 160 million years, is a remarkable tale of evolutionary innovation, ecological success, and, ultimately, extinction. The age of flying reptiles reached dramatic heights, but like countless other ancient creatures, these magnificent animals faced a crescendo of extinction waves, culminating in the devastating end Cretaceous catastrophe. This chapter explores the stages of pterosaur decline, the survivors who managed to endure, and the final cataclysm that closed a glorious chapter in Earth's history. Throughout their history, pterosaurs endured multiple environmental fluctuations and extinction pressures. The Permian-Triassic extinction had preceded their rise, and across the Mesozoic, changing climates, sea level variations, and shifting ecosystems continually reshaped their worlds. Despite their adaptability and diverse capacities, these stressors periodically caused declines in populations or lineages, with evidence in the fossil record of localized extinctions and turnover between species. By the late Jurassic and early Cretaceous, pterosaurs had diversified into an array of families, including the spectacularly large ajdarchids and specialized groups like pteranodontids and tapagerids. Yet even here, signs emerge of ecological competition, especially with the rise of early birds. These more agile and rapidly reproducing avian species began to encroach on aerial niches, creating selective pressures that likely influenced pterosaur diversification rates, feeding strategies, and behaviors. The fossil record from the mid to late Cretaceous reveals a gradual narrowing of pterosaur diversity, particularly among smaller species. Many small-bodied pterosaurs appear to have vanished, potentially outcompeted by birds adapted to similar roles in insectivory and small prey hunting. In contrast, large azhdarchids persisted and even flourished, dominating aerial and terrestrial niches. Their enormous size and specialized biology may have offered some advantages amid changing ecosystems. However, the very gigantism that epitomized the apex pterosaurs could have contributed to their vulnerability. Larger body sizes generally involve slower reproduction rates and higher energy demands, making ecosystems more susceptible to collapse when resources become scarce or environments rapidly fluctuate. The final and most cataclysmic blow to pterosaur existence came with the Cretaceous Paleogene (KPG) extinction event approximately 66 million years ago. Triggered by a massive asteroid impact near present-day Chicxulub, Mexico, combined with prolonged volcanic activity and climate instability, this event caused widespread environmental devastation, dramatically altering global ecosystems. Pterosaur fossils abruptly vanish from the record following this extinction event, signaling their complete disappearance from the Earth's fauna. Unlike their dinosaurian cousins, birds, which survived and diversified, pterosaurs left no living descendants. The reasons likely include a combination of factors: their specialized life histories, competition with birds that rapidly expanded after the KPIC, and ecological disruptions that shattered their feeding and breeding grounds. Despite extinction, pterosaurs' legacy remains profound. Their reign demonstrated the biological potential for vertebrate flight and the evolutionary experiments in size, anatomy, and ecology that nature can achieve. Their disappearance marks a pivotal shift in Earth's flying vertebrate dominance, turning the skies over to birds and setting the stage for new evolutionary radiations. This extinction story underscores the deep interconnection between life and Earth's dynamic forces. It prepares us to explore the lasting influences of pterosaurs on modern science, culture, and our understanding of life's resilience and fragility in the next chapter. A legacy that continues to inspire and inform. The pterosaurs, the pioneering masters of Mesozoic skies, have left a legacy that resonates far beyond their extinction millions of years ago. Their story, one of evolutionary innovation, ecological dominance, and eventual disappearance, continues to intrigue scientists and captivate popular imagination. This rich legacy encompasses profound impacts on modern science and an enduring presence in culture, education, and art. By exploring the multifaceted ways pterosaurs influence contemporary understanding, we appreciate how these ancient creatures still shape our perspectives on life, flight, and the natural world. In the realm of science, pterosaurs have been central to expanding knowledge of vertebrate evolution, biomechanics, and paleo-environments. Their unique anatomy challenges traditional concepts. Unlike birds or bats, pterosaurs evolved powered flight through an elongated fourth finger supporting a membranous wing, a design astonishingly different, showcasing nature's versatility in solving the problem of flight. Paleontologists study pterosaur fossils to unlock mysteries of flight mechanics, respiratory systems, growth patterns, and sensory capabilities. Through advancing technologies, such as laser scanning, computerized tomography, and aerodynamic modeling, researchers recreate detailed images of pterosaur anatomy and behavior, refining ideas about their ecology and physiology. These studies not only illuminate pterosaur biology, but inform broader fields such as evolutionary biology, functional morphology, and even robotics, where biomimicry takes inspiration from pterosaur flight for drone design and micro-air vehicles. Pterosaurs also serve as critical markers in stratigraphy and paleoecology, helping scientists date geologic formations and reconstruct ancient environments. Their fossils provide windows into the climates, ecosystems, and faunal communities of the Mesozoic, fostering understanding of Earth's dynamic history and informing models of biodiversity through time. Beyond academic circles, pterosaurs have imprinted deeply on popular culture, fueling imaginations through media, literature, and art. From early 20th century scientific illustrations to their blockbuster portrayals in films and documentaries, pterosaurs have been iconic representations of prehistoric life. Their dramatic wingspans, peculiar crests, and uncanny blend of reptilian and bird-like features make them endlessly fascinating symbols of adventure and discovery. Museums worldwide showcase pterosaur skeletons, animatronics, and immersive exhibits, inspiring generations to learn about Earth's prehistoric past. Artistic renderings, painting, sculpture, digital animation bring these creatures alive, sparking curiosity and understanding beyond scientific papers. Their cultural depiction also raises questions about scientific accuracy, encouraging dialogue about evolving knowledge and science communication. In education, pterosaurs offer compelling gateways to teach concepts of evolution, anatomy, physics of flight, and environmental change. Their story integrates multiple disciplines, stimulating student engagement and interdisciplinary learning. Educators leverage pterosaurs' captivating appeal to explore topics from fossilization processes to advanced engineering principles. Moreover, pterosaurs have inspired creative expression and storytelling, appearing in novels, comics, video games, and even music. These representations celebrate the grandeur and mystery of flight, the awe of ancient life, and the timeless fascination humans hold for creatures that shaped our natural heritage. However, the legacy of pterosaurs is also a sobering reminder of extinction and environmental fragility. Their disappearance at the end of the Cretaceous echoes contemporary concerns about biodiversity loss and ecosystem disruptions. As such, pterosaurs serve as ambassadors of deep time, helping society contextualize current environmental challenges within the grand arc of Earth's history. Through integrating scientific insight with cultural resonance, the legacy of pterosaurs underscores the enduring power of ancient life to inform, inspire, and challenge humanity. Their wings echo across disciplines and imaginations, reminding us of adaptation's complexity, evolution's creativity, and the delicate balance sustaining life. As we conclude this series on the age of flying reptiles, we reflect on how pterosaurs, masters of the ancient skies, changed life on Earth forever. Pioneers of flight whose story is still being told, studied, and celebrated in the unfolding narrative of our planet's history. Reconstructing the past is both the art and science that allows us to journey back millions of years and bring ancient worlds vividly to life. For pterosaurs, creatures that vanished at the close of the Cretaceous period, this endeavor weaves together fossil discoveries, advanced laboratory techniques, and cutting-edge technology. Through these methods, modern scientists breathe life into fragile bones and shadowy impressions, transforming scattered fragments into comprehensive portraits of these remarkable flying reptiles. The journey begins with fossilization, the remarkable natural process that preserves traces of life for millions of years. Pterosaur fossils are often delicate. Their skeletons, adapted for flight, were thin-walled and fragile, making their preservation a rare and precious occurrence. Fossilization typically occurs when an animal dies, and its remains are swiftly buried by sediment in environments such as river deltas, lagoons, or shallow seas. Over time, minerals seep into the bones, replacing organic material and hardening into stone, while sediment layers compress and preserve the shape and sometimes even soft tissue impressions. Across the world, renowned fossil beds like Germany's Solnhofen limestone, Brazil's Santana Formation, and China's Jehol biota have yielded exquisitely preserved pterosaur specimens. These sites provide not only bones, but occasionally soft tissues, such as wing membranes or traces of pycnofibers, that offer extraordinary insights into pterosaur biology. Once fossils are excavated, vertebrate paleontologists undertake painstaking preparation, delicately removing matrix and other encasing rocks with micro-tools, air abrasives, and sometimes acid baths. The goal is to reveal and conserve every minute detail while preserving the specimen's integrity for study and display. Modern laboratories employ a suite of analytical techniques to reconstruct pterosaur anatomy and lifestyles. Computed tomography, CT, scans generate detailed three-dimensional images of fossil interiors, unveiling internal bone structures, brain cavities, and muscle attachment sites without damaging specimens. These digital models can be manipulated to understand biomechanics, revealing how joints moved or how flight muscles operated. Microstructural analysis of bones, histology, allows scientists to study growth patterns, age, and life history. By slicing thin sections of fossil bone and examining them under microscopes, researchers discern growth rates, maturity stages, and even metabolic implications, connecting function to form in deep time. Chemical analyses, including isotopic studies, illuminate diets, migration patterns, and environmental conditions pterosaurs experienced. For example, ratios of oxygen isotopes in fossils can suggest climate and water temperatures, while carbon isotopes offer clues about food sources and trophic levels. In parallel, biomechanical modeling and computational fluid dynamics simulate flight performance. Using fossil data to recreate wing shapes and muscle capacities, scientists generate aerodynamic models that explore how pterosaurs soared, took off, and navigated wind currents. These simulations enhance understanding of their flying capabilities and ecological niches. Paleontologists also collaborate with artists, applying these scientific findings to create accurate yet imaginative restorations. Digital reconstructions and physical models bring pterosaurs to life in museums, films, and educational materials. This interplay of science and art aids public engagement, fuels inspiration, and enriches both scientific communication and popular culture. The process of reconstruction is iterative and ever-evolving. New fossil finds continuously inform and sometimes challenge existing interpretations, while advances in technology expand our capabilities. Molecular paleontology, though in early stages for such ancient specimens, offers tantalizing possibilities for understanding pterosaur soft tissues and pigmentation. In essence, reconstructing the past from fossilization to the modern lab is a multidisciplinary endeavor. It synthesizes geology, biology, chemistry, physics, and artistic vision to unlock the stories encoded in stone, transcending millions of years to connect us intimately with the age of flying reptiles. As we look ahead, the exploration of recent discoveries and emerging technologies promises to deepen our grasp of pterosaur life and evolution, constantly breathing new life into the ancient skies they once ruled. The study of pterosaurs continues to be a vibrant and rapidly evolving field, propelled by a wave of recent discoveries that have dramatically deepened our understanding of these ancient flying reptiles. Across the globe, new fossils and cutting-edge technologies are reshaping long-held assumptions and opening fresh avenues of inquiry. This section explores how recent findings, enhanced analytical techniques, and innovative interdisciplinary approaches are revolutionizing pterosaur paleontology. In the past 2 decades, significant fossil discoveries in regions like China, Brazil, and Morocco have yielded exceptionally preserved specimens that offer insights into pterosaur physiology and diversity previously unimaginable. For example, the Jehol biota in northeastern China has produced exquisitely detailed fossils showing not only bones, but also soft tissues, such as wing membranes, muscle fibers, and pycnofibers, the fuzzy integumentary covering akin to protofeathers. These specimens have illuminated debates about thermoregulation, flight capabilities, and the evolutionary relationship between pterosaurs and other archosaurs. Notably, some fossils demonstrate evidence of coloration patterns through the preservation of melanosomes, microscopic pigment-bearing organelles. This has allowed scientists to infer color and iridescence, suggesting that pterosaurs might have displayed vibrant hues for social signaling or camouflage, adding a new dimension to understanding their behaviors and ecology. Elsewhere, discoveries of embryonic and juvenile pterosaurs in exceptional detail have enriched knowledge about growth rates, developmental stages, and reproductive biology. Fossil nests with eggs and hatchlings show early flight capabilities, challenging traditional views about parental care and life history strategies. In addition to exciting new fossils, technological advancements have revolutionized data acquisition and analysis. Micro-CT scanning allows non-destructive, high-resolution imaging of internal structures within fragile fossils, revealing the morphology of brain cases, inner ears, and air sac systems. These insights inform reconstructions of sensory capabilities, neurological function, and respiratory physiology. Three-dimensional computer modeling and finite element analysis have become indispensable in simulating pterosaur flight mechanics, bone stress distribution, and muscle function. These simulations provide robust data on how pterosaurs launched, glided, maneuvered, and coped with aerodynamic forces, frequently challenging earlier, less detailed interpretations. Isotopic analyses using stable isotopes of oxygen and carbon contribute to understanding pterosaur paleoecology, such as their habitat preferences and migratory behaviors. By examining these chemical signatures found in fossilized remains, scientists can reconstruct ancient climates and diets with increasing precision. Moreover, advances in phylogenetic methods, integrating vast datasets of morphological and molecular information, refine pterosaur evolutionary relationships and clarify their position within Archosauria, helping resolve long-standing debates. Interdisciplinary collaboration between paleontologists, engineers, computer scientists, and artists has fostered innovative approaches, blending empirical data with visualizations and functional models that bring pterosaurs vividly to life for both scientific communities and the public. While these advances have answered many questions, they have also sparked new debates and mysteries, propelling the field into new frontiers and continuing to captivate researchers worldwide. As we progress to the exploration of unresolved questions and current scientific debates, the rapid development of knowledge underscores the dynamic nature of paleontology and the enduring fascination with the age of flying reptiles. Pterosaur paleontology, though rich with remarkable discoveries, remains a field rife with intriguing debates and unsolved mysteries that challenge scientists and fuel ongoing research. These enigmatic aspects of pterosaur biology, evolution, and ecology highlight the complexity of interpreting ancient lives from fossil fragments, encouraging continuous re-examination of evidence and opening new horizons for understanding the past. One of the central debates revolves around the precise evolutionary origins of pterosaurs. While it is broadly accepted that they belong to the Archosauria, their closest relatives within this group remain uncertain. Various hypotheses propose ancestral links to different basal archosaurs or close kin to dinosaurs, but the scarcity of transitional fossils leaves the question open. New fossil finds or molecular insights could one day clarify the exact evolutionary pathway that led to their unique adaptations for flight. Another persistent mystery concerns the nature and extent of pterosaur integument. The discovery of pycnofibers has suggested a complex covering potentially analogous to early feathers, possibly serving roles in insulation or display. Yet, debates continue about the diversity, structure, and evolutionary significance of these fibers, including how they compare to feathers in dinosaurs and birds. The precise implications for pterosaur metabolism, thermoregulation, and the evolution of endothermy remain topics of active inquiry. Flight mechanics and behaviors also inspire lively discussion. While models and fossil anatomy provide general frameworks, questions linger about the nuances of takeoff strategies, wing loading limits, flight endurance, and maneuverability, especially in the largest species. How colossal pterosaurs like Quetzalcoatlus managed energy-efficient flight and balanced terrestrial movement remains an area of exploration, blending biomechanics with environmental reconstructions. Pterosaur social behaviors and communication present another frontier. The function of elaborate cranial crests and ornaments, whether for sexual selection, species recognition, or aerodynamic purposes, invites varying interpretations. Moreover, the extent of vocalization, visual signaling, and sociality is yet to be fully understood, limited by fossil evidence, but inferred through comparative anatomy and behavior of modern analogs. Reproductive biology continues to offer tantalizing puzzles. Although nesting sites and egg fossils have been found, details about incubation methods, clutch sizes, hatchling development, and parental care strategies differ among species and are subject to ongoing study. How pterosaurs balanced reproductive needs with their demanding aerial lifestyles is an exciting question bridging paleobiology and evolutionary ecology. The biogeographical patterns of pterosaurs raise further questions. Disparities in diversity and morphology across continents call for investigations into dispersal routes, habitat preferences, and responses to geological changes like continental drift and climate shifts. The relationship between environmental dynamics and pterosaur evolution remains a fertile area for research. Finally, the reasons behind their extinction spark important debates. While the Cretaceous-Paleogene event is the obvious culprit, understanding why pterosaurs failed to survive when birds thrived is complex. Factors such as ecological competition, reproductive strategies, body size, and habitat loss interplay in hypotheses still under examination. Overall, these debates and mysteries not only highlight gaps in our knowledge, but also emphasize the dynamic, evolving nature of paleontology. Each discovery prompts new questions and refines scientific narratives, ensuring that pterosaur research remains a vibrant and compelling pursuit, bridging ancient history with modern curiosity. As we turn next to the artistic interpretations of pterosaurs, we will examine how science and creativity combine to bring these ancient flyers to life in vivid and inspiring ways, weaving together evidence and imagination to celebrate their enduring legacy. Artistic interpretations have played a pivotal role in shaping our collective vision of pterosaurs, elevating these ancient flying reptiles from fragmented fossils to vivid, dynamic creatures that captivate the imagination. Through the combined expertise of paleontologists, illustrators, digital artists, and museum designers, pterosaurs have been brought to life in ways that enrich scientific understanding, inspire curiosity, and immerse audiences in the prehistoric world. This chapter explores the multifaceted relationship between art and science in pterosaur reconstructions, acknowledging how evolving evidence continually influences their portrayal in media and museums. From the earliest scientific illustrations, artists faced the challenge of interpreting limited fossil data, often filling gaps with imaginative guesswork informed by contemporary knowledge of reptiles and birds. Initial depictions in the 19th and early 20th centuries represented pterosaurs as bat-like, copying known mammalian flyers, or as awkward gliders with membranous sails. These images, however speculative, laid the foundation for public fascination and provided starting points for further inquiry. Advancements in paleontology, powered by field discoveries and refined analytical techniques, invited more accurate and nuanced artistic renderings. Artists began incorporating detailed anatomical knowledge, such as bone structure, wing membrane attachment, and evidence of pycnofiber coverings, resulting in more lifelike and plausible representations. This transition marked a crucial alignment of science and art, where illustrations became critical visual hypotheses that complemented research. The rise of digital technology has revolutionized pterosaur artistry, enabling the creation of highly detailed three-dimensional models used in museum exhibits, documentaries, and virtual simulations. Digital artists collaborate closely with scientists to incorporate accurate anatomical features, plausible coloration based on fossilized pigments, and realistic environmental contexts. These renderings allow viewers to visualize flight dynamics, behaviors, and ecological interactions, transforming static fossils into living entities. Museums have embraced these artistic interpretations through immersive exhibits featuring animatronics, life-sized sculptures, and interactive displays. Exhibitions often include soaring or perched pterosaurs amid naturalistic backdrops, helping visitors grasp scale, movement, and ecological roles. Such installations enhance educational impact, providing tangible connections to deep time and evolutionary history. Beyond museums, pterosaurs have been recurrent stars in documentaries, films, books, and educational media. Their dramatic forms and pioneering flight inspire storytelling that blends spectacle with science, engaging broad audiences worldwide. Popular culture thus acts as a bridge, translating complex paleontological research into accessible and compelling narratives. However, the relationship between artistic interpretation and scientific evidence is dynamic and sometimes contentious. As new discoveries emerge, artistic depictions must evolve accordingly, challenging previous assumptions and correcting misconceptions. For example, the recognition of pycnofibers transformed portrayals from smooth-skinned reptiles to fuzzy, warm-blooded creatures, influencing perceptions of their physiology and behavior. Collaborations between artists and scientists foster dialogue that balances creativity with rigor, emphasizing that all reconstructions are best viewed as informed interpretations, subject to revision. This approach encourages critical thinking and appreciation for the scientific process, highlighting how art can visualize hypotheses while inviting further exploration. In essence, artistic interpretations serve as vital portals connecting the ancient past to modern audiences. They humanize extinct life, animate fossilized remains, and facilitate understanding of pterosaur biology and evolution. Through ever-improving technologies and interdisciplinary partnerships, these portrayals will continue to evolve, enriching our connection to the mesmerizing age of flying reptiles. As we approach the concluding reflection on how the age of pterosaurs changed life forever, we recognize that their echoes persist not just in rocks and bones, but also in the imagination and creativity of humanity. A lasting legacy carried forth on the wings of art and science alike. The age of flying reptiles, ruled by the pterosaurs for over 160 million years, represents a defining epoch in Earth's biological and evolutionary history. The impact of these extraordinary creatures extends far beyond their own existence. It echoes through the corridors of time, influencing ecosystems, evolutionary pathways, and even the way humanity understands the natural world. As we contemplate the legacy of the pterosaurs, we discover how their mastery of the skies forever altered life's grand narrative. The pterosaurs were the first vertebrates to achieve powered flight, pioneering an aerial realm that until then had been limited primarily to insects. Their evolution fundamentally changed the dynamics of ecosystems, introducing new predator-prey relationships, novel ways of exploiting resources, and opening up ecological niches that reshaped the planet's biotic communities. By conquering the air, pterosaurs joined and expanded the web of life, connecting terrestrial, aquatic, and aerial environments in ways unimaginable prior to their emergence. They acted as apex predators, scavengers, and opportunistic feeders, influencing populations of fish, insects, small vertebrates, and even shaping the vegetation indirectly through their role in seed dispersal or predation. The flight adaptations of pterosaurs also set precedents that echoed in their dinosaurian cousins and ultimately in birds. Their unique wing structures, supported by elongated digits and membranous coverings, showcase evolutionary experiments in biomechanics and physiology, broadening our understanding of how diverse life can innovate solutions to common challenges like takeoff, maneuvering, and energy efficiency. Their rich diversity, from diminutive, agile flyers to colossal giants with wingspans rivaling modern aircraft, demonstrates life's remarkable capacity for adaptation and specialization. The proliferation of pterosaur species across all continents underscores their success and ecological importance pre-extinction. Though pterosaurs vanished at the close of the Cretaceous, their extinction paved the way for birds to rise and diversify, inheriting the aerial domains. This transition exemplifies the dynamic flow of evolution, where extinction and emergence occur in an endless sequence, shaping the ongoing saga of life on Earth. Beyond science, pterosaurs inspire wonderment, curiosity, and creativity in human culture. Their forms, behaviors, and stories continue to influence art, literature, film, and education, igniting imaginations and bridging ancient worlds with modern minds. Thus, the echo of their wings is not merely a chapter confined to fossil records, but a lasting resonance that shapes how we perceive evolution, adaptation, and the interconnectedness of all life. The age of flying reptiles forever changed life on Earth, not just through flight itself, but through the profound transformations that mastering the skies enabled, a legacy perpetually unfolding in the history of nature and humanity alike.